everyone, welcome to this bridge class. Today's topic is Introduction to Aeronautical Engineering. Now do not worry, even if you are not an aerospace major, you can understand this class. Now, let's get ready and step into this beautiful aviation world. These are the topics we'll be covering today. From the introduction, I'll talk a bit about the history of aviation, and then there's the anatomy of the airplane, which is the basic structure of airplanes. The fourth is basic aerodynamics, some easy physics, don't worry. And last, there are pop quiz and conclusion and recaps. Let's start with the introduction. First of all, welcome to this class. I really hope you'll enjoy this short class, and I hope you can know a little bit more about aeronautical engineering after this. If you don't mind, can you share some first thoughts when hearing aeronautical engineering? Is it Boeing, NASA, or spacecraft? In fact, this is a branch of engineering focused on the design, development, and testing of aircraft and spacecraft. Aviation started a long time ago, long before we were born, and this era has advanced a lot through those years. We all know the history of the Wright brothers. They are the first ones that had a successful and sustained flight in history in the early 1900s. But what about before? Who paved the way for them? From 1486 to 1490, Leonardo da Vinci left more than 500 sketches of his design, but the approach to flight proved to be unsuccessful over the ensuing centuries. In 1783, the Montgolfier hot air balloon floated over Paris. This was the first time a human being was lifted and carried through the air for a sustained period. George Cayley is the first person to propose the fuselage idea. We'll talk about the fuselage later. He also proposes separate mechanism for the generation of lift and propulsion. Later in the 1870s, Philip de Temple and Alexander Misasky invented the first two power hubs in history, but this is still not sustainable flight. Later in the 1890s, very soon, Otto designs the fully successful gliders. He makes more than 2,000 flights. And last, 1903, the Wright brothers sustained secure and successful flight. For all this help, especially from Glenn Curtiss, the Wright brothers, and Langley's work, modern aviation has a solid foundation, and so they are called the aeronautical triangle. Part 3 is the anatomy of airplanes. In this part, we'll learn about the basic structure of airplanes. Here's a simplified version of the airplane, but I know it's a lot. There are some nouns we do not understand, so let's break it down into smaller parts. Here are the four forces on an airplane. Thrust is provided by engine, and there is the gravitational force of weight. These two are easy to understand. For lift is the force that directly opposes the weight of an airplane and holds the airplane in the air. Lift is generated by every part of the airplane, but most of it is by wings. And last, the drag. Drag is the aerodynamic force that opposes an aircraft's motion through the air. Drag is the mechanical force generated by a solid object moving through a fluid. It's kind of like the skin friction between the molecules of the air and the solid surface of the aircraft. Here are the structures that are associated with the four forces we talked about. Well, it seems easier when we know the function, right? It's just different names. Wing and jet engine are to generate. Flap, spoiler, slat, and aileron are for pilots to alter concerning their necessities. Rotation are also crucial for airplanes. Have you ever wondered how the airplanes change directions? There are three axes: roll, pitch, and yaw. Here is a short video for your better understanding. With these three axes, an airplane can move in the direction it requires. Going back to the basic structure, these 5 elements are the components that control roll, pitch, and yaw. Suddenly, it seems easier, right? Horizontal stabilizer and vertical stabilizer, like the name, for the stability of an aircraft, and for rudder, elevator, and aileron, are mostly used by pilots if they want to change direction. Last, the airfoil. Frankly speaking, an airfoil is the cut of the wing, and there are different dimensions of it. For instance, the mean camber and chord could be different, leaving a variety of airfoils. And there is NACA, followed by 4 or 5 digits number. For example, NACA 2412. Part 4 is basic aerodynamics. It's just easy physics, don't worry. Consider it as storytelling. One of the most important concepts is the continuity equation. The laws of aerodynamics are formulated by applying several basic principles from physics to a flowing gas. For example, mass can be neither created nor destroyed. To apply this principle to the flowing gas, consider an imaginary circle drawn perpendicular to the flow direction, as shown in this figure. Now look at all the streamlines that go through the circumference of the circle. These streamlines form a tube, called a stream tube. As we move along with the gas confined inside the stream tube, we see that the cross-sectional area of the tube may change, say, is in moving from point 1 to point 2 in the figure. However, as long as the flow is steady, which means invariant with time, the mass that flows through the cross-section at point 1 must be the same as the mass that flows through the cross-section at point 2. Because, by the definition of the streamline, there can be no flow across streamlines. The mass flow through the stream tube is confined by the streamlines of the boundary, much as the flow of water through a flexible garden hose is confined by the wall of the hose. This is a case of what goes in one end must come out the other end. Let A1 be the cross-sectional area of the stream tube at point A. Let V1 be the flow velocity at point 1. Now, at a given instant of time, consider all the fluid elements that are momentarily in the plane of A1. After a lapse of some time, dt, these same fluid elements all move in the distance v1 dt as shown in this figure. In so doing, the elements have swept out a volume A1 v1 dt downstream of point 1. The mass of gas dm in this volume is equal to the density times the volume, that is, dm equals rho 1 A1 v1 dt. This is the mass of gas that has swept through area A1 during the time interval dt. Definition: the mass flow m through area A is the mass crossing A per unit time. Therefore, from the last equation for area A1, mass flow equals dm over dt equals m1 dot equals rho 1 A1 v1 dt, and the unit is kg over s or slugs over s. Also, the mass flow through A2, bounded by the same streamlines that go through the circumference of A1, is obtained in the same fashion as m2 dot equals rho 2 A2 v2. Because mass can be neither created nor destroyed, we have m1 dot equals m2 dot. Hence, rho 1 A1 v1 equals rho 2 A2 v2. This is a continuity equation for steady fluid flow. It is a simple equation that relates the values of density, velocity, and area at one section of the stream tube to the same quantities at any other section. The string tube sketches in the last figure does not have to be bounded by a solid wall. For example, considering the streamlines of flow over an airfoil as sketched in this figure. This is a string tube. The string tube sketched in the last figure does not have to be bounded by a solid wall. For example, consider the streamlines of flow over an airfoil as sketched in this figure. The space between two adjacent streamlines, such as the shaded space in this figure, is a string tube. Equation low AV equals low AV applies to the string tube in this figure, where low 1 and V1 are appropriate means over A1, and low 2, V2 are appropriate values over A2. And this is the end of the physics lesson. There are more concepts and equations you need to learn, like energy equation, momentum equation, or compressible and incompressible flow, but you'll learn it afterwards. Part 5, Pop Quiz. You'll learn some fun facts about airplanes. Question 1. Which spot is the safest to see on an airplane? Countdown for 5 seconds. The answer is D, at the back of the aircraft. Why? The back of the aircraft is typically safer because it's further from the impact zone during a crash, and the tail section tends to remain more intact, according to tons of air accident references. But don't worry, air accident occurs much less than traffic accidents. Question 2. How much time do oxygen masks provide oxygen on an airplane? Take a wild guess. The answer is B, around 10 to 15 minutes. Airplanes provide a limited amount of emergency oxygen to give passengers and crew time to manage an emergency descent to a safe altitude where they can breathe without supplemental oxygen. So don't worry, the crew can control this incident in a short period. The last part is the conclusion and recap, some objectives for you. We talked about the aeronautical triangle, the 4 forces, rotation, and the continuity equation. As the famous saying goes, I fly because it releases my mind from the tyranny of petty things. I hope you can find peace and broaden your mind after this small lesson. Here's a resource list. Thank you for listening to this lesson with me and hope you have a great day.